All right, hi everybody. Happy Monday. We are video recording today. One of the students is in the hospital for a few days and can't come to lecture. And if this works, I'm hoping this works pretty well. I'll just be posting this on a public YouTube page, and there will be a link to it, as always with things in this class. Things pertaining to what happened in class on a certain day, you can find in the calendar on the entry for that day. So you'll be able to just go to the calendar entry for today and find a link to the YouTube video. Gabriel will be careful to not get any of your faces on the video, so I'm not asking your permission. You're just going to get me. If you are in the witness protection program, as I know that some of you are, your secret's safe. You won't be ratted out by this video. All right. So we are starting Stewart section 2.4, which is the product and quotient rule. So I'm going to just dive right in. So meeting part one is the product rule. So the product rule is for finding the derivative of a product of functions. So something of this form, f of x times g of x. So that's a product. So if you park in front of this, the derivative symbol, that means that you're going to take the derivative of that product. And what this rule says is you do the following. You do the derivative of the function on the left, and then you just multiply that by the function on the right, not the derivative. And then you add to that the left function, not its derivative, times the derivative of the function on the right. So that's the product rule. It's not terribly hard. We're going to get to much harder rules. But already it's tricky because the thing that is obvious to do when you want to take the derivative of a product is actually the wrong thing. So observe. If I have a product, and I'm going to take the derivative of that product, I don't do this. I don't do the derivative of f of x times the derivative of g of x. This would be really cool. It would say the product of a derivative, the derivative of a product is the product of the derivatives, but that's not true. So you have to be very careful. So this is the thing that is kind of automatic, and it's the wrong thing. So, for example, find the derivative of f of x equals square root of x sine of x. So notice that's a product of functions, but also notice that the symbol f of x is being used for the whole function. F of x is not being used for the function on the left. F of x is the whole thing. So when you use these rules, you have to be careful. You have to notice that sometimes the things that you're going to be applying these rules to are not going to have these names. So here we go. We're going to start. Our left side is going to be f prime of x. So that's going to be the derivative of this thing, square root of x sine of x. And we're just going to use the product rule. We're going to do the derivative of square root of x times sine of x plus square root of x times the derivative of sine of x. And I don't need to say this, but I will. And of course, simplify. In this course, we always simplify. All right, now notice that the product rule doesn't tell us what those derivatives are going to be. So when we use the product rule, it just gets us to here. We're going to be doing some derivatives. Now I'm going to put parentheses around these places where these derivatives are going to happen because I find it helpful to first of all write down the stuff that's not going to change. So in the next step, there's going to be some parentheses times the sine of x. There's going to be plus square root of x times some parentheses. So those parentheses are where we're going to put the results of those derivatives. So, easier one. Who can tell me what goes in these parentheses? Good, cos x. I'm going to go for broke. What goes in these parentheses? Anybody know what goes in these left parentheses?
1/2 x to the power of negative 1/2.
Okay, 1/2 x to the power of negative 1/2. But that's not simplified, right? Let's check this out. So we have the dirty word. The derivative of square root of x, that's the derivative of x to the 1/2. So that's 1/2 times x to the 1/2 minus 1. So that's 1/2 x to the minus 1/2, which is as far as you got. But that's not simplified. In this course, we can't leave this in this form. That's 1/2 times 1 over x to the 1/2. That's 1/2 times 1 to the square root of x. So in other words, 1 over 2 square root of x. We've done this derivative a few times last week. So all that stuff could be off to the side. So 1 over 2 square root of x. So I can simplify this as sine x over 2 square root of x plus square root of x times cos x. Example 2. Can I erase this up here? Find the derivative of 5x cubed. So, we have our enthusiastic students, Frick, Frack, and Wacky Jack. They're all going to try their hand at this. So here's Frick. Here's Frack. And here's Wacky Jack. All right, who has comments signs on these three solutions: fricks, fracks, wacky jacks. Got one hand up. More hands. Who's right, who's wrong? Yeah.
I believe Wacky Jack is correct.
Wacky jack and frack got the same answer. Any other observations? What's wrong with frick?
He didn't do the product rule correctly.
He didn't do the product rule at all. He did, actually, we don't know anything about frick. They did this. They did the product of a derivative is the derivative of a product is the product of the derivatives. That's not the product rule. So it's not that Frick didn't do the product rule correctly. Frick just didn't do the product rule. This is not true. Again, the derivative of a product is not just the product of the derivative. Now, what did frac do here? It's just the product rule, right? Now, let's go on. Did frac do, oops, this should say, now did frac do this step correctly? So I got three equal signs here. Is this equal sign valid? Yeah. How about this equal sign? Yeah. So it's a product. It's a product of functions, the constant function and the x cubed function. And you can use the product rule in that. How about wacky jack? What did wacky jack use?
The power rule.
Later, first use the constant multiple rule. Because the 5 is actually a constant multiple. You can think of it as a constant function if you want. You can use the product rule. And then here, Wacky Jack used the power rule. So notice the work that Wacky Jack did is this work. I mean, the frac did that work over on the right side of their solution. But frac also did this. Now I'll tell you, in the heat of quizzes or exams, students will often make a mistake. They'll say the derivative of 5 is 5, or they'll say the derivative of 5 is 1, or they might say the derivative of 5 is 5x. There are all sorts of ways to make a mistake in this step. So even though the product rule is not killer, this gives you opportunities to make a mistake. And I mentioned last week, when we learned the sum rule and the constant multiple rule, I said we're going to be learning more complicated rules. But if there's ever a situation where you can use the sum and constant multiple rule, that's the best rule. Because notice, Wacky Jack did the least work. So not only did they do less work than frac did, they did not have the opportunity to make a mistake. Is the sign-in sheet making its way around somewhere? Who's got the sign-in sheet? Way back there. Everybody sign in? Anybody not sign in? Right. Okay, meeting part 2 is what's called the quotient rule. So the quotient rule is used for finding the derivative of a quotient. Now when I write quotients, I actually use descriptive names. So instead of using f and g as I did in the product rule, I use top x and and bottom of x. So there's a quotient of functions. So what if we had to find the derivative of this? Well, that would be the following. You find the derivative of the top function, so top prime, and you multiply that by bottom. And then you subtract. Subtract top times the derivative of the bottom. And then you divide the whole thing by the bottom function squared. And I put the bottom function in parentheses and I square it. So that's the quotient rule. Now, just as over here, remember with the product rule, there was an obvious thing that was the wrong thing. The derivative of a product is not the product of the derivative of the derivatives. The derivative of a quotient is the derivative of top over bottom is not equal to top prime over bottom prime. Again, the derivative of a quotient is not equal to the quotient of the derivative. All right, example 3. Find the derivative of f of x, which is this function, f of t, which is 2t over 2 plus square root of t. All right, so Frick does the following, gets the answer 4 square root of t. Frac does this. F prime equals the derivative 2t times 2 plus square root of t minus 2t times the derivative of 2 plus square root of t, all divided by 2 oops, I have this upside down. Sorry, my bad. Broke my function upside down. F of t is 2 plus square root of t all over 2t. Sorry about that, very sorry. So f prime, according to Frick, is this, the derivative of 2 plus the square root of t divided by the derivative of 2t. And so then Frick gets 1 over 2 square root of t, because of that calculation we did a while ago, divided by the number 2, so that's 1 over 4 square root of t. Frac does this, the derivative of 2 plus the square root of t, all of that times 2t, minus quantity 2 plus square root of t times the derivative of 2t, all divided by 2t quantity squared. Okay, so then they go on. Remember, the derivative of 2 is 0. The derivative of square root of t is 1 over 2 square root of t. So that's in the upper left corner. And then this is being multiplied by 2t. In the upper right, you get the quantity minus the quantity 2 plus square root of t times the number 2, because the derivative of 2t is the number 2. And on the bottom, the quantity 2t squared is going to be 4 times t squared. Now we can simplify this. Notice that these 2's cancel. And what's t divided by square root of t? T divided by square root of t. Thought you were going to answer. Do you know? Yeah. Well, say it again? No, not quite.
T to the 1 half.
Yeah, it's just the square root of t. Yeah, that's t to the 1 divided by the t to the 1 half, so I end up with square root of t in the upper right corner. And then I get minus 4, and then I get minus 2 square root of t, and that's all divided by 4t squared. You got to keep simplifying. Square root of t minus 2 square roots of t give me minus t minus 4 all over 4t squared. That's frac. Wacky Jack. Starts by doing this. First, rewrite f of t in power function form. So f of t is 2 plus square root of t over 2t, but I can write this as 2 over 2t plus square root of t over 2t. But those 2's cancel, so I get t to the minus 1. And over here I get 1 half times 1 over square root of t. But that can be simplified. That's not in power function form yet. One half t to the minus 1 half. Notice Wacky Jack has not found the derivative. They've just rewritten the function. Now find f prime. So f prime of t is going to be the derivative of that. So the derivative of t to the minus 1, we can use the sum and constant multiple rule. So the derivative of t to the minus 1 plus 1/2 times the derivative of t to the minus 1/2. Notice the sum and constant multiple rule does not tell us what those derivatives are going to be. It just tells us that those are going to be the derivatives we should do next. So those are going to be power rule derivatives. So they're going to get minus 1 times t to the minus 1 minus 1. They're going to get plus 1/2 times minus 1/2 times t to the minus 1/2 minus 1. So that's minus 1t to the minus 2, and this is minus 1/4 t to the minus 3/2. But remember, we have to simplify. We can't leave things with negative exponents. So Wacky Jack goes on and does this. Minus 1 over t squared minus 1 over 4 t to the 3/2. All right, frick, frack, Wacky Jack. What do you think of these solutions?
Frick is not correct because you just took the derivative of the top and then divided it by the derivative of the bottom.
Yeah, so Frick did the same thing that they did up there. Frick said the derivative of a product is the product of the derivatives. That's not true. Now remember, the derivative of a quotient is not the quotient of the derivatives. So Frick is batting 0 for 2. This is not true. All right, everybody wake up. Turn off your phones. The derivative of a product is not the product of the derivatives. The derivative of quotient is not the quotient of the derivatives. A lot of you will get caught by this. You want to make sure you're awake and your phones are off and you pay attention to this, because it's a very common mistake to do what Frick did. What about what Frack did? What rule did Frack use?
The quotient rule.
Yeah, which makes sense because we have a quotient. All right. Anybody see any problems with Frack's work? There's not really any problem with Frack's work. How about Wacky Jack? Very different. Wacky Jack and Frack use about the same amount of chalk. What's the hardest rule that Wacky Jack used? Well, just the power rule. So remember my slogan, if you have a situation where you can use the sum and constant multiple rule and you can use simpler rules, use simpler rules. So notice that Wacky Jack did a lot of stuff, but it was all kind of simpler stuff. I'm rewriting this in power function form. That's all prerequisite stuff. I mean, it's not to say that it's easy. So, a Wacky Jack had 1, 2, 3 steps of rewriting the function before they even started finding the derivative. But then the derivative was pretty simple. And then they had some steps of rewriting the result. But wait a second, why did Wacky Jack and Frack not get the same answer?
Because Frack is much, well, it's because Frack's equation is a much more, or unsimplified version of the Wacky Jack's thing.
In what way?
I believe you need to do, you have to put Frack's in power notation, I believe.
Right, so Frack's not done simplifying here. So let's break this up into two things. This is minus square root of t over 4t squared minus 4 over 4t squared. So simplify more. t on top and t squared on bottom. That's t to the 1/2 power, t to the 2nd power here. So the difference of those is 3/2. So this is minus 1 over 4 t to the 3/2. Again, t squared, t to the 1/2. So you take the difference of those, the highest one is at the bottom. And then over here, the 4's cancel. You have minus 1 over t squared. It's the same answer. So Frac didn't realize that they were not done simplifying. So they had to do a bunch of simplifying steps. They did it at the end, and their derivative was hard. So might as well do the simplifying at the beginning to make the derivative easier. So this happened last week. Remember last week we had a derivative that looked like a quotient. And I said, we don't know the quotient rule. When you learn the quotient rule, you can use the quotient rule on this, but trust me, it's harder. It's always easier to use the simpler rule. So always, whenever, if you can use the sum and constant multiple rule, use it. So if you're just given these instructions, find this derivative, then do it the easiest way. If you're told find this derivative using the quotient rule, then you've got to do a fraction. But if you're not told what method to use, just use the easiest method. Example. Yeah.
Over there, it's on the bottom of the quotient, it says, the ratio, it says bottom of x squared, and then I see bracket that put the top squared on the bottom.
No, I remember I had originally written this problem wrong. Yeah, so the bottom is 2t. So example 4, find the derivative of g of t. Now we're going to have 2t on top and then 2 plus the square root of t on bottom. So notice that g is just the reciprocal of f. Well, g prime of t is the derivative of this thing, 2 over 2 plus the square root of t. Now, notice this cannot be rewritten in that simple way. So Wacky Jack can't work their magic here. There's no getting around the fact that you have a quotient and it can't be written in a simpler way. So you have to use the quotient rule. So this can't be, g of t can't be simplified. So be on the lookout. Your homework in section 2.3 and 2.4. Well, in both of those sections, you have some functions that are presented to look like quotients. But to find the derivatives is actually simpler to rewrite the functions first, and then find the derivatives using simpler rules. But in your section 2.4 problems, where you've learned the quotient rule, you do get some derivatives. This is actually one of them. This is one of your homework problems. Find this derivative, and you just have to use the quotient rule. Example 5. Everybody scoot up next to somebody. There should be pairs of you. So if you're sitting by yourself, find a partner. We have another loner over here. One of you join over here in the third row. Take 2 plus 2. Good. Okay, everybody's in groups of 2. So you're going to do 2 examples. I find the derivative of tangent of x. All right? And then you're going to go right on in your pairs. Sit in pairs. Any of you ever do study abroad? Any of you going to do study abroad? When? Where are you going to go? Because you could go to Paris. You could be right now having instructions sit in Paris and do this. But here you are in the basement of Bolton Hall. Example 6. Let f of x be this function, 1 over 1 plus x squared. I'm going to shut up. You can just get to work on that problem. I'm going to be writing problem number 6 out.
Yeah. And then you just have to whatever cosine is over cosine is.
Yes, derivative of the sine times cosine minus the derivative of cosine times sine.
Yeah.
And then that's all of them for cosine.
The thing of sine
The derivative of sine is just cosine. The derivative of cosine is negative sine.
Yeah. Great. Yeah, I think, yeah.
I think that's if you do cosine,
Oh, yeah. Yeah, so I think it just be 1 over cosine squared.
Isn't that also sine? Yeah.
I don't know if you want this to be. I think we
Yeah,
should start.
Yeah.
Derivative of 1 times 1 plus x squared. So we have to find A's final derivative. So you could do the quotient and do the derivative times 1 plus x squared minus 1 plus x, or no, the derivative of 1 plus x squared times 1.
Yeah.
Everybody sign in? Anybody not sign in?
Yeah, yeah, yeah.
I just didn't synthesize the bottom.
That's fine.
Yeah, I think that's just the. This whole thing. But
Well, the thing is, really, is like minus. What is it again? How do you get to equation?
oh, it's 1 minus. So like if you have a point, let's say you have a point like 2.
Very discreetly raise your pinky if you solve exercise 5.
Times x
So,
minus 2. Yeah, but we don't have 1. So,
I feel like this is.
but we can plug in.
yeah, because
All right. I'm going to go through these now because there are enough pinkies in the air, and if I wait too long, they're going to be in people's noses. So here we go. So the derivative of tan x, the key thing is that you remember what tan of x is. That's the derivative of sine of x over cosine x. So we have to use the quotient rule. So we do the derivative of sine of x, the derivative of the top, times the bottom, minus the top, times the derivative of the bottom, all divided by bottom squared. Now it's common for books to write cos squared x. I like writing cosine of x in parentheses squared. Okay, I'm going to do the same thing that I have done before. I'm going to write down the stuff that's not going to change. I'm going to have parentheses times cos x minus sine x, parentheses, all divided by cos x in parentheses squared. Hey, can I cancel cos x here? Why not?
Because cosine of x and then cosine of x squared is 3. Right.
They're not that different. Like x over x squared. Actually, they're very much the same. So why can't we cancel? That's why I'm bringing this up. Yeah. Yeah. Exactly. There's no cos x over here. Well, there's one that's inside that derivative sign. But so the big warning here, Gabriel said not to use red chalk. So warning, you cannot cancel cosine of x here. In all of these quotient rule problems, you can't cancel the thing that's sitting there. There you've got bottom, and there you've got bottom squared. You can't cancel because there's no bottom over here. All right, what goes in this parentheses? Somebody on the north side over here. What goes in these parentheses here? One more try. Good, cos x. All right, you can redeem yourself. What goes in these parentheses? Good, negative sine of x. So when I simplify, I always have to simplify. I get cos x squared plus sine x squared all over cos x squared. I can simplify that further. Who can tell me how that simplifies? Got one hand up.
You can write cosine squared over cosine squared plus sine squared over cosine squared.
Okay, could do that. I'm gonna do that over here. Break this into 2. do next?
That equals 1 plus tangent squared. Like,
Yeah, that's just 1, and this is tangent of x squared. What's another way of rewriting this?
Cosine x squared plus sine x squared equals 1.
Yeah. So this is 1 over cos x squared, but that's the same as 1 over cos x, that whole quantity squared. What's another name for 1 over cos x?
Secant.
Secant. So this is secant of x quantity squared. That's an identity. Secant of x squared is 1 plus tangent of x squared. So in your book now, you've got a whole bunch of new derivative rules enabled by the quotient rule and product rule involving trig functions. You can look up those in the list. Okay, we have just 9 more minutes. I want to get to some interesting stuff. So I want to skip ahead on A. F prime of x is the derivative of 1 over 1 plus x squared. Now, notice that's not something that can be rewritten. So we have to use the quotient rule. Anybody get this? Be really subtle. Say, I got it, if you got it. Anybody get this? Okay, I'm gonna just go ahead and give you the answer, because I want to make sure that you get to the, what?
I didn't understand what happened. I think I have.
Oh, you didn't yell it, yell.
I got it.
Good, all right. All of your classmates resent you. All right, what's your answer?
Negative 2x over 1 plus 2x squared plus x to the 4.
Yeah, now I'm going to leave the bottom simple. Minus 2x, and on the bottom I'm just going to write 1 plus x squared. There's the bottom squared. You could write that as 1 plus 2x squared plus x to the 4th, but I find this simple. Still worth a round of applause. All right, B. Who can tell me what we need to build here? So the question is, find the equation for the line tangent to the graph of f at x equals -1. So I always start this out the same way. I say we need to build parts.
Build the equation.
What's the equation?
Y minus y of a equals y prime of a. That's fine, right?
Yeah, and I always use the letter f. I do y minus f of a equals f prime parentheses a times x minus a. All right, so now we need to get parts. Somebody who's wearing green. What is a? Good. And what's the significance of that number? What is that?
That's our x value.
Yeah, it's the x coordinate of the point of tangent. Say again?
The x coordinate of the
Yeah, which is the point of tangent, right. And so our f of a, f can be f of minus 1. So that's, I go get my function, 1 over 1 plus, how would I do? What is this expression here?
Undefined.
Well, this thing right here.
That's just 1 squared. Negative 1.
Okay, so then I would have 1 plus a negative 1, that would be 0. I'd have a 0 in the bottom, which is undefined. So what's the problem here? What did I do wrong?
put parentheses or.
Yeah, if I want to square the negative 1, I've got to do this. Because otherwise, order of operations says you square the 1 and then you stick on the minus sign. I don't want to do that. I want to leave the minus sign on there and square it. So that's f of a. Now, what's the significance of that?
The y value of the point of tangents.
Yeah, it's the y coordinate of the point of tangency. And then f prime parentheses a, that can be f prime parentheses minus 1. So I have to go get my formula for f prime, which is there. So I get minus 2 times minus 1 over 1 plus, in parentheses, minus 1 squared. And then that's being squared. So the minus cancels. I end up with a 2 on top. And on the bottom I have 1 plus 1 squared. So that's 2 over 4. So that's 1/2. And that's, what's the significance of that? Well, it's the same value, but what's the significance of f prime parentheses a? Somebody whispered it. Somebody whispered it again. Slope of the tangent. So we put all these parts together. So y minus f of a, so it's y minus 1/2 equals f prime of a, so that's that 1/2 times x minus a. It's x minus 1. X minus 1. So that's 1/2 times x plus 1. So that's 1/2 x plus 1/2. So when I put this in slope-intercept form, I get y equals 1/2 x plus 1. Here's my equation. Who can answer question C? Question C says, find the x-coordinate of all points in the graph that have horizontal tangent lines.
Just set it equals 0.
Set what equals 0?
Then you just or no, not that. Wait, no, yeah, you said that equals 0.
That would find the x-intercept of the tangent line. But the question is, find the places on the graph where the graph has a horizontal tangent line. This line is not horizontal. So it's definitely not at x equals -1. Yeah. Yeah, so C, set m equal to 0. So f prime of x equal to 0 and solve for x. So let's turn this around. 0 equals minus 2x over 1 plus x squared. How are we going to solve that in 1 minute? Got one hand up. What has to be true for a ratio to be 0? You have to have the numerator must be 0. And what else must be true? The bottom can't be 0. Well, so what x values make that true? So the solution is x has to equal 0, because that's the only thing that will cause the numerator to be 0. Now, we're out of time, but let me show you this graph because it's really cool. If you make a table of values, it's not hard, but I ran out of time. So this is D and E. Now, I like this kind of problem. It's the kind of thing that they don't ask you in web science or in the book. But it's a great way to wrap up this question. This is the graph of f of x equals 1 over 1 plus x squared. It goes through the point 0, 1, because when x is 0, y is equal to 1. And look, the tangent line, sorry Gabriel, I'm going to get out the red chalk because tangent lines look great in red. That we found that when x is minus 1, y is 1/2. So minus 1, 1/2. So there's an xy pair. And here's the tangent line. This is the line that's tangent at x equals -1. And this is the line that has equation y equals 1/2 x plus 1. Notice the y-intercept of this line is the number 1. It goes through that point. It's not tangent there. It's tangent here. Notice it's kind of going the same direction as the graph at that point. Now the other question was, find the x-coordinates of all points that have horizontal tangents. This is the one that's really cool because it's really easy to see. Look at this. The line that is tangent here is that. At x equals 0, there's a horizontal tangent. Isn't that pretty? So this is a really cool function. It's not that hard to make a table of values and graph this function. And you get a much better understanding of these tangent line problems. You can see there's only going to be one tangent line that is horizontal. There's only going to be one x value that causes that numerator to be 0. All right? Thanks, everybody. I'll see you. You'll see Gabriel tomorrow on presentation. Gabriel, thanks for reporting.